Next speaker that I'm delighted to introduce is Ivan Minchev, who's going to be speaking about a geometry of cubic discriminants in 8 dimensions. Take it away.
Thank you very much. I'm very grateful for the invitation. Special thanks to Jan, sorry. I like very much the conference and of course the city. Being again here after a few years, it's a big pleasure for me. So my talk is based on a joint work with Elisa Hristova from Sofia University, so from Sofia. So it's going to be so we are interested in Riemannian manifolds, 8-dimensional Riemannian folds that admit reduction of the structure group to from SO8 to the reducible SO4. So the problem is in a way similar to the geometry of the reducible SO3 in dimension 5 that was introduced by Bubinsky and Nurovsky in 2005. So I will just mention a few facts first about this case, the reducible SO3 in dimension 5, because it will help to get the right perspective what we're doing. So very briefly, so what Bubinsky and Nurovsky showed is that in order to reduce the frame bundle of Riemannian manifold to SO3 reducible in dimension 5, one needs a tensor field, a totally symmetric tensor field in the manifold. So it's equivalent. The reductions are equivalent to the existence of such a totally symmetric tensor field in the manifold that has some special properties. So the properties are easy to this. Well, at least the first two is quite easy to understand. So, as I said, totally symmetric tensor. All the contractions must vanish, and then there is a third quadratic condition, which looks a bit more complicated. But speaking in general terms, so we multiply the tensor gamma by itself, and then we take certain contraction to this object, and then we symmetrize, and what we get is that in a way everything simplifies, so the result is given entirely in terms of the metric tensor of the manifolds, vaguely speaking. So that's the result of Bubinsky and Nurovsky. And so going back to what we're interested in, so we would like to consider SO4 in dimension 8, the reducible SO4 in dimension 8. So we show that the reduction to this subgroup is actually equivalent to the existence of a certain rank 4 tensor on the manifold, which in a way, I would explain how exactly in a second, which in a way is given by the formula for the discriminant of a cubic polynomial. So just recall. So if we have a cubic polynomial, say in the variable z, and a, b, c, d are the coefficients, complex coefficients in general, so we have some homogeneous polynomial in degree 4 in these variables a, b, c, d. And the way we like to think about this discriminant actually is of course, we can think of this as a totally symmetric 4 tensors defined on C4. So C4 being given by the coefficients of the polynomial. So this is the way we would like to think about this formula. And so the first thing I would like to here to observe is that some basic facts about the reducible action of SO4 on R8. So it is. So we consider just a vector. So R8, we fix the metric, we fix orientation. So we have SO8, and if we take a subgroup of SO8, which is isomorphic to SO4 and acts reducibly on R8, then it's quite a simple observation that you can always find in between of these two a copy of SP2 times SP1. So it's a famous group that actually is related to the Quaternion-Keller geometry in dimension 8. and this copy is unique. So it's very easy to see why is this so. So we just start by decomposing SO4 as a product of two SP1s. And the reducible action on R8 is such that exactly one of these SP1 copies in SO4 acts reducibly, and the other one acts irreducibly. So we take the one that acts reducibly on R8, and then we take its centralizer. It has to be isomorphic to SP2, and then the product of these two gives us this red object, this copy of SP2, SP1 that always stays in between. So what does this mean geometrically? It means that when we consider reduction, many fold with reduction to the structure group to SO4, then we always have an underlying reduction to the larger group, SP2, SP1. This means that on such manifolds, we always would have an underlying almost quaternion Hermitian structure. So it comes for free. So in other words, what we do, in order to define a reduction to SO4, we need to start with an almost quaternion Hermitian structure first, and then consider some further conditions. So that's the way we go. So let me first recall what an almost quaternion Hermitian manifold is. So that's the underlying structure. That's a Riemannian manifold with a rank 3 subbundle of the endomorphism bundle, such that locally this subbundle Q is generated by 3 almost complex structures that satisfy the quaternic identities, and they are of course compatible with the metric. So 3 almost Hermitian structures satisfying the quaternionic identities, and that's the name quaternion Hermitian. Of course, an almost quaternion Hermitian manifold is called quaternion Keller if it's integrable. So this means that the Levitshev-Gitte connection of the metric G needs to preserve this subbundle Q, and is called hyperkeller if, of course, we can find such local basis of almost complex structures that are parallel with respect to the Levitshev connection. But this is the terminology that's used. So this is our underlying structure on the manifold. So now, in order to explain further how we get the reduction from SP2, SP1 to SO4, some basic algebraic facts, which are well known. All of them are well known, but I just want to give you the right perspective. So we just first look at C4 as a representation of the symplectic group, complex symplectic group. So we have a 2 form that's invariant. And then we have the compact form of this complex group, SP2. Of course, W will be for me in the whole talk. W will be just C4, the representation C4 of SP2 or the symplectic group. It doesn't matter. And then we have the complex conjugated to this, the conjugated representation W bar. And if we take the sum of these two, then we get an 8-dimensional representation. Then the compact form of the symplectic group just can be seen as the stabilizer of a Hermitian scalar product. So a map from W bar to R. So in other words, so all this is of course well understood, well known. I'm not saying anything new, but I want to just to fix the notation and to explain this clearly. Now V will be for me the real part. So of course W plus W bar has an obvious conjugation on it. So we have a real structure. So we can think of this 8-dimensional complex vector space is the complexification of a certain 8-dimensional real vector space, which will be V for me in the talk. And then, of course, SP2 is just the stabilizer of the 2-form P that descends to V, and of the inner product, compatible inner product G that we have on this vector space. And then, of course, we automatically get also a triple of almost complex structure on this vector space, J1, J2, J3. Very easy. So J1 just corresponds to the splitting WW bar. This should be the eigenspaces for J1. J2 we obtain by playing with P and G, so G times J2 should give us the 2 form. Pi is the 2 form, so the invariant 2 form on V, and then J3 is just the product of J1 and J2. So all these are sp2 invariant objects on our 8-dimensional vector space V. So, and now we are interested in another representation of sp2, namely the space of all hyperkähler curvature type tensors on the vector space V. So here we mean the algebraic, purely an algebraic way the hyperkähler curvature type tensors. So we mean all tensors K, which are skew symmetric in the first two and last two arguments, satisfy the Bianchi identity. So this is an algebraic equation, and then so they take value in sp2. This is the second condition. So it's again a representation of sp2. I shall denote this representation by H. sp2 is important for the talk. And it is well known that as a representation of sp2, this actually space is isomorphic to the symmetric, to the space of all totally symmetric 4 tensors on W. So that's the key point here, because you recall the discriminant of a cubic polynomial is actually something that lives here. So this is the way how we lift it to an 8-dimensional real vector space, so by this isomorphism. So now we can think of the discriminant of a cubic polynomial as a hyperkähler curvature type tensor on an 8-dimensional real vector space. Yeah. And of course, so I was speaking about just the formula for the discriminant, but in fact this is a whole orbit, because so after change of the basis with sp2, I obtain many other such tensors. So we get an orbit, an sp2 orbit in this space of all hyperkähler curvature type tensors. And each element of this orbit, so we will call just cubic discriminant. So this is, let's say, totally symmetric 4 tensor. For example, if you want to think of the discriminant as symmetric tensor, then it's totally symmetric 4 tensor for which there exists special basis, so basis, compatible basis with the action of sp2, so that this tensor would be the discriminant of a cubic polynomial with respect to this basis. So that's how we can think of this. And so we denote this sp2 orbit by C. So the set of all cubic discriminants, of course, it's a sp2 orbit, and it's an easy observation that, of course, it will be the quotient of sp2 by the stabilizer of an element in this orbit. And it turns out that the stabilizer of an element in this orbit is sp1, but a copy of sp1 in sp2 that acts again irreducibly on V. So that's why this notation. It's quite easy to understand why is it so. So we think, we think of W as polynomials, cubic polynomials, right? W are cubic polynomials, so it means, well, they are cubic polynomials of one variable, or equivalently, they are cubic polynomials of homogeneous polynomials degree of 2 variables. So this means that we identify W with the symmetric third power of over these 2 variables, so C2, and C2 is a representation of sp1, and in this way sp1 actually acts also on W. So W is a reducible representation of sp1, and of course it's in the stabilizer of the cubic discriminant, and it's a bit more work just to show that it's precisely the stabilizer. So that's the cubic discriminants are just this homogeneous space. So the first natural question that arises, and so sounds quite classically, is if we are given, let's say, a totally symmetric 4 tensor over C4 or over W, or a cubic or a hyperkähler curvature type tensor, doesn't matter on the real space, or a-dimensional real space. So the question is, when is so to find some algebraic characterization without referring to a special basis, the existence of a special basis, so that it would look like a cubic discriminant, but just purely algebraic conditions that would ensure this the existence of such a special basis. So I didn't find a reference to this. I tried to find, but I was not successful. So we had to answer this ourselves. But it's quite a straightforward, a clear answer to this, at least. So the answer sounds like this. So if we are given such a totally symmetric fold tensor on W, then there are two quadratic conditions that are equivalent to the property that S is a cubic discriminant. So they look quite messy maybe here, but I will explain them more geometrically in a minute. So the first is that I multiply the tensor S by itself, and then I take two constructions, and this should simplify. Pi here is the 2 form. So we're working with symplectic representation, so we have an invariant 2 form. That's what pi is. And the second formula is even messier than the first one. So because we take the tensor product, we take only one trace, some other terms, and then we take the symmetrization over the free indices, not all the three free indices, 4 of the 5 free indices. So it is what it is. So this is this characterizes the cubic discriminant. It is a bit more enlightening if we think in the real situation, so on the real H space V. So if we think of the cubic discriminants as hyperkähler curvature type tensors on the real H space V, so of course hyperkähler curvature type tensor is the same as a certain map from symmetric map from the real algebra SP2 to SP2. And just to be more precise, I shall denote this induced automorphism of SP2 by tau subscript k. So if k is a cubic hyperkähler curvature tensor, type tensor on V, then tau k is the corresponding automorphism of SP, a symmetric automorphism of SP2. And then k is a cubic discriminant. So the characterization is, so we have two conditions. One is that the first is easy to understand here because it just says that k should have fixed eigenvalues, nothing else. And the second is shows how actually this automorphism is related to the Lie algebra brackets in SP2. So this second formula, which was much messier before, and this can be understood in this way. So how the automorphism is related to the Lie algebra bracket. So one important consequence of this proposition is that actually all the conditions here involved in describing the cubic discriminants, they don't use the almost complex structures J1, J2, and J3. So we have V is SP2 representation, so we have these three complex structures there. But we don't use them. We just use the Lie algebra bracket on SP2, which means that actually this orbit, the cubic discriminants, are preserved by the larger group, actually. Not only, sorry, I pressed something, yes, by the larger group SP2, SP1, not only SP2. So we can enlarge this group by one more factor SP1. And then looking at the stabilizer of the cubic discriminant in this larger group, we find out that this is exactly SO4 irreducible. That's how SO4 actually comes into the whole thing. So just the stabilizer of a cubic discriminant in this larger group. So summarizing all that I have said so far, it's easy to summarize. So we have a geometric interpretation of this homogeneous space. So this is just the set of all cubic discriminants on V. So these are all hyperkähler curvature type tensors that are given by the formula for the cubic discriminant with respect to some special basis. That's the geometric interpretation of this homogeneous space. So now I would like to see a bit what happens on the side of the differential geometry from here. So suppose that we are given an almost quaternion Hermitian manifold. Then, of course, at each point of the manifold, we have the set of all hyperkähler curvature type tensors that are cubic discriminants. So it's a canonical object. So this could be described also as the set of all hyperkähler curvature type tensors, so that the induced automorphism of sp2 has these properties.
So you mean only in dimension 8?
I'm sorry?
So you are only in dimension 8 here?
Only in dimension 8, not nowhere else, yes. No, it doesn't work anywhere else, so only in dimension 8. And then of course we have a canonical fiber bundle with 7-dimensional fibers, so it's 7. And the sections of this fiber bundle are, we call just cubic discriminants on the manifold. And from the whole construction, it is clear that having a cubic discriminant on an 8 manifold, on an almost quaternion Hermitian manifold, is the same as having a reduction to the SO4 irreducible because of this algebraic procedure which I described before. These are just tautology, so there's nothing more to say about it. So we just write it as a definition. So an SO4 irreducible structure on 8 manifold would be just a pair first of an almost quaternion Hermitian structure and then a fixed global section of this bundle of the cubic discriminants or cubic discriminant. So that's the interpretation. And so it turns out that there are, of course, you have plenty of examples of such structure because you just take any almost quaternion Hermitian manifold and any section of this bundle, so there are many. But there are a few interesting examples which have been they're interesting by many reasons, which I would like to explain, and they are based on the Lie group G2. So there are two Lie groups, two real Lie groups of type G2. We have the compact one and the non-compact, which I denote by G22. The second two being the signature of the killing form, and it turns out that each of these, one is compact, of course, the other is non-compact, and each of these Lie groups contains a copy of SO4, and that acts irreducibly on the orthogonal, so on an 8-dimensional vector space. That's the orthogonal, the killing orthogonal complement of SO4 in the Lie algebra. And it is well known, so there are two symmetric spaces. One is one of the Wolf spaces, and the other, I think, was first considered by Alexeyevsky, so it's known as the Alexeyevsky space. And so these homogeneous spaces, they carry a homogeneous quaternion Kähler structure. So M1 is the Wolf space, and it has positive scalar curvature. Of course, it's compact. And the other one is non-compact. It has negative scalar curvature. So these are two examples, and both of these actually have natural homogeneous cubic discriminants defined on them. I will explain this immediately. So we just take the complexified Lie algebra, and then we can pick a basis for this Lie algebra. So in the following way. So the irreducible SP1 inside, we just take a basis by, so of course, Psi1, Psi2, Psi3, then the reducible part by phi, and then by phi, and then there is some 8-dimensional complement for which we use E alpha and E alpha bars, alpha being an index between 1 and 4. Then we have the obvious conjugation, because of the obvious conjugation I mean that these are real. The first 6 are real, and then E alpha by the conjugation will be mapped to E alpha bar. And the obvious conjugation defines the compact form of G2. So this is one way to see it. And if we would like to obtain the non-compact form, The only thing that we need to change in the conjugation is to add one minus. So E alpha bar should be mapped to minus E alpha bar. That's the easiest way to write these two real forms of the complex G2. And then how to see the cubic discriminant here. So the adjoint action of this psi s on this eight-dimensional complement, it actually preserves the linear span of the E alphas without the bars. And it is 4 times 4 matrix, that's denoted by gamma s. And then it turns out that if I multiply each gamma s by itself, and then sum over s, so that will be a tensor which is symmetric in alpha, beta, and gamma delta automatically. But then the totally symmetric part of this is exactly what is given exactly by the formula for the cubic discriminant. So it appears automatically, and then you get another part which is given by the two-form pi, which we always have. So because we are speaking about symplectic things. This is how the cubic discriminant appears, and it is of course parallel with respect to the Levi-Civita connection on this group. So moving one step back, going back in a more general situation. So let me recall that in general, if we have a quaternion-Keller manifold, so these two were quaternion-Keller manifolds, so in general, if we have any quaternion-Keller manifold, then the curvature of, it's well known that this curvature splits in a sum of two components. One with subscript h is just a tensor that has the algebraic properties of a hyperkeller curvature, and the other is some fixed tensor, which is essentially the curvature of the quaternion projective space, and it can be explicitly expressed by the metric and the local basis of the almost complex structures, which I denote here by IS. So it's a very well known. That's a thing that it's actually the way you prove that it's always Einstein every quaternion-Keller, because this has no trace and all the trace is due to this, and you get automatically this Einstein and constant. Of course, the scalar curvature is always a constant. Well-known things. But so what I want from here is just also to recall some very basic fact about quaternion-Keller manifolds, namely that if you of course assume that the first component, this hyperkeller curvature type component, vanishes, then you can say exactly what the manifold is. So it depends only on the scalar curvature. So you have either the projective space, or you have the quaternion hyperbolic space if the scalar curvature is negative, or you have R8, so the flat space. So so the first component vanishes, so it's very easy to say what the manifold is. So now the natural question to ask is what happens if this first component does not vanish, but is actually proportional to a cubic discriminant. So this is one of the results which we have obtained. So this also has a clear answer. So if the first component in this decomposition of a quaternion-Keller manifold, is proportional to a cubic discriminant where f is any function on the manifold, then it turns out that this function needs to be always constant, and then the manifold is either the non-compact quotient of G2 over SO4. This is if the function is positive, and if the function is negative, then it has to be isometric to the other one, to the Wolf space. So these are the only two possibilities. It's not isometric but homothetic, because you need to rescale, of course, the metric. So it's not only one, but so this is one of the results that I wanted to present. And another thing, again, supposing that we are given any almost quaternion-Hermitian manifold. Now we don't speak about quaternion-Keller necessarily, but any. And then, well, it's a standard procedure. It's nothing special, but of course, it works here as well. It is standard procedure of producing a unique connection that preserves this cubic discriminant of the structure. So it works. So there is such a unique characteristic connection, intrinsic connection, something called. We have constructed it, so it has torsion. And in general, this torsion has many components, of course, because well, the assumptions are very low. But if you assume that the underlying structure is quaternion Hermitian, then the torsion is reduced only to 4 components, so it's much smaller. And here in dimension 8, it makes sense to assume something actually in between. This also is something specific only for dimension 8, that it's possible to have a dimensional almost quaternion Hermitian manifold with closed fundamental 4 form, which is called also harmonic, which is not parallel. This doesn't happen in higher dimensions, so this is only in dimension 8. So if you assume this is also interesting, so you get more components, of course, but about twice as many components of the torsion of this intrinsic connection. I'm not going to go into this more because it's not that important. What I want to say is what happens actually, what are the integrable geometries? So what are geometries where the torsion of this connection actually vanishes? And this also is not probably very surprising. It turns out if we have an integrable cubic discriminant anomalous quaternion Hermitian manifold, then M has to be locally actually homothetic, not isometric, but doesn't matter. So it should be locally equivalent in a way, either to the whole space or to this Alexeyevsky non-compact version of it. Or it has to be the flat space, of course, depending on so there are only these 3 possibilities. So this might sound surprising, but not actually if you think of this from the other perspective. There is a theorem of Bergy that says that it's a list of possible holonomic groups, and of course SO4 irreducible is not in that list. So this means that all geometries with groups that are not in that list need to be either locally symmetric or products, so they have to be a finite number. So this means that if we are interested in such non-standard groups, then always the integrable case will be described by finitely many examples. So the proof is also based kind of this idea. So the structure, so to say, the structure equation for this group are much stronger than for the groups in the list of the Bergy. So you consider the first Bianchi, the second Bianchi, and they're too strong, and they kill all the curvature, so you get the result like that. So this was my talk. Thank you for your attention.
Let's see if there are any questions from the speaker.
Did you find some topological structure?
That's a good question. We haven't. We didn't go that way, but it's for the SO3 reducible is an interesting thing, and yes. So I can say a bit. So maybe one thing. So if you want to find maybe topological abstraction, it's good to consider the twistor space. I mean, it almost because on the twistor space this. So you, so to say, you have 8-dimensional real vector space, and if you want to have it split as W and W bar as it was in the beginning, then you will have to go to the twistor space. There you have natural splitting of the tangent space in W and W bar, and then topology would come from this, that you need to find another 2-dimensional SP1 bundle over the twistor space, so that this W, which is a 4-dimensional bundle, will be the symmetric third power. And from there, probably you can get some topological abstraction, but I haven't done this, so I don't know.
If I remember, you have already for SP2, SP1 from each other. Here, you have all the topological abstractions by an old paper, 10 years old, 20 years old. So already, because you have SP2, SP1 structure plus this section, this special section from CW to W, then in a sense, you can get these topological abstractions and try to finally find topological abstractions for your section, for this special section.
Yeah, there should be further topological abstraction than just SPF. I expect that, but I don't know. I haven't done it.
I have also another question.
Mm-hmm.
There's no relation with spin 7 geometry because it's not inside there. In spin 7 it's inside SO8, but your SO4 doesn't live inside spin 7, right?
Yeah, no.
So you didn't find some connection with spin 7 geometry?
No, not. I can't. I don't see any relation.
Right.
So it's interesting. Maybe it's more natural to look the relation to this 235, for example, geometries, because they again live on G2 by some parabolic subgroup. That's more It's more promising probably if one wants to find connection to something else, but I haven't done it yet.
SP1 contained spin 7?
No, it's not. Neither inside G2. SP2, SP1 is not inside G2, right? No, because otherwise...
No, it's not, yes.
No, it's not. So it's not neither inside spin 7. Yeah.
Okay.
Okay, thank you.
There are no more questions. Let's thank Ivan again. Oh, no more questions. Yeah.
So in the case of this, at the very end, integrable cubic K, so this integral means,
That there exists torsion-free connection. If it's torsion-free, it's called the Levi-Civita because the metric should be preserved as well. So it's about the Levi-Civita.
And a very short question, maybe you can then move it to other time, but how did you end up in the SO4, SO8 case? So you have tried some original situations, or you have directly focused on this SO4, SO8 case? Because you have mentioned during the talk that it doesn't work in
Yeah, well, I wanted specifically to look at SO4 reductions of SO8. And then I came to a formula by some symmetric polynomial, and then I realized it's the cubic discriminant, so that was the way.
But the initial motivation was to...
I wanted to see what happens, yes, with the SO4 irreducible.
the idea
Curious.
to identify algebraically some structures.
Yeah, to see what kind of geometry, what kind of connection, what kind of components. And actually, one of the motivations originally was that, so you have this, as I said, yeah, in the harmonic case, so you don't have that many examples. So I was hoping by adding such additional nature of restriction to be able to find at least homogeneous, so easier to calculate by this additional. So this was the original way I started. So, but I haven't gone that way, very far in this direction. But I plan to. So that was.
All right, now it looks like there are no more questions. Let's try clapping again.